Hi, welcome to the video solution for past paper. This is Edexcel IAL Physics Unit 2 new specification, and this is specimen paper of Unit 2. So let's start. Question number 1, which of the following is a unit of frequency? So frequency, generally unit is hertz, but hertz is not given. So you need to see the formula for frequency. The simple formula for frequency is F equal to 1 upon T. T is, this is time and measured in seconds. So this is 1 upon second or second inverse. So second inverse is the unit. So option is C. Which of the following properties is not shown by longitudinal waves? Longitudinal waves are the waves in which oscillation of the particles are parallel to the direction of motion of a wave. So wave is moving horizontally. This is wave moving horizontally. So particle oscillating also parallel, meaning horizontally. If waves goes left or right, so particle remains parallel to the direction of motion. That means this behavior of the wave, we say that it cannot be polarized. So polarization cannot be defined and cannot be shown by the longitudinal waves. Longitudinal waves, you can say longitudinal waves does not show polarization. The diagram represents the position of particles before a progressive wave passes and at a particular instant as the wave passes. So we have undisturbed medium, normal pressure, we have some disturbed medium, wave is passing. Which of the following graphs correctly shows the variation of pressure with the distance from x as the wave passes at the instant shown? So you see that we are giving 4 different options, and generally this is the compressional waves. So this rear fraction is considered as low pressure. It is low pressure, and this one is high pressure area. And that means you don't waste time thinking about A and D. The reason is in the graph, because you see the y-axis is increasing pressure, and this is the normal pressure in that moment. So for X, you see here you have high pressure region, so you cannot have option A and D. So you need to think the difference between B and D. Indeed, you have high pressure region and pressure is increasing upward. So definitely it should be some high pressure value. So your option should be B. Question number 4. A slinky spring is stretched a total length L from one side of a classroom to the other. The tension in the spring is T. A wave pulse travels along the spring with the velocity V. The spring is taken to a sports hall and stretched to a total length of 2L. Length is double, and the tension which is also double. Which of the following gives velocity of the wave pulse along the spring? So we need to find new velocity. So you know that in case of a string or a spring, if we have a tension, some tension, then speed is T by mu. That's how we can define V. So if tension is T and length is L, then the speed is V. So I am assuming the new speed is V dash when the length is increased double and tension is double. So V dash would be equal to T dash new tension and mu. So now you see how can you figure out this? So this mu is mass per unit length, which is m upon L. So you can rewrite this formula as, just ignore this, you can rewrite this formula as T by m upon L, and L comes up, so TL over m. That's how, this is the velocity. Now tension is double, so new velocity is V dash, and tension is double, 2T, length is also double, 2L, divided by mass of the spring stays same. And now clearly you can see that 2 times 2, 4. 4 comes out from the root. So twice of the TL upon M. And this TL upon M is your old velocity when you have t and l. That means v dash is equal to twice of the v. That's how you can figure out your option, which is D. There is a potential difference of 6 volt across a 4 ohm resistor. A charge of 5 coulomb flows through the resistor. Which of the following is the energy transferred by the resistor? So energy is E is equal to VIT, generally a general formula, voltage, current and time. So we are given voltage, we are given resistor, but we don't have time and we don't have current, but V and I is charge per unit time, and time goes, so E is equal to VQ. That means you don't need the resistor to find the energy transfer, because you have charge, of course, and you have a voltage. You multiplied these two, you can have energy. So V is 6 and 5 coulomb. So 6 5 times 5 times 30, so 30 joule. Option is D. Question number 6. Which of the following will have the largest de Broglie wavelength? De Broglie wavelength, remember, lambda is equal to h upon p or h upon mv. That means lambda is proportional to 1 upon p, or inversely proportional to the momentum, or you say lambda is inversely proportional to the mass and lambda is inversely proportional to the velocity. So in order to observe de Broglie wavelength, mass should be very small, velocity should be high. That's how you can visualize, or you can detect, or we can detect de Broglie wavelength. So what are the options? An electron moving at almost high speed, it should be the option, because electron is the lightest particle, because proton is heavy, tennis ball, athlete running. So all these three masses are quite big, and of course yeah, you can say the speed, but mass is big. So electron moving at almost speed of light, so mass is small, speed is very high, so your option should be A. The formula sheet contains the formula I is equal to NQVA, where I is the current through a sample of a material. Which two quantities in the formula are related to resistivity of the material? If you see resistivity, that we generally use letter rho. Resistivity is constant for a given material, for a given material. That means different materials have different rho, different resistivity. Copper has different resistivity, iron would have different value, aluminum different resistivity. That means it all depends on types of material, types of the material from which the material is made of. So that means it's all depends on how many electrons are there, or what is the speed from the material. That means resistivity depends on uh, charge carrier, charge density, and the speed. So your option should be C. Which graph correctly shows how the potential difference V varies with the current I for a filament bulb? So it is all about filament bulb, and remember, for filament bulb, as current increases, so temperature increases, so resistance always increases. This is the relation. Current increases, current keep increasing, that causes temperature to increase, and due to increase in temperature, resistance also increases. And now we are given VI, all are VI graph. V on the y-axis and I on the x-axis. And if you have a V and I graph, then gradient of the graph will be equal to the resistance, because the gradient is V upon I. You see that, rise over run, V upon I. So that means gradient of all the curves are showing the resistance. So if you see the first one, a straight line, the gradient constant, that means resistance constant, which is not possible for filament bulb. And here gradient is decreasing, so resistance is decreasing. So of course it cannot be the filament bulb. Indeed, option should be C, because if you follow the curve, gradient of the curve is increasing, that means resistance increasing. So it should be your option C. Question number 9. Huygens constructions can be used to explain what happens to a wave when it meets an obstacle. Which diagram is correct attempt to use Huygens construction to predict the position of the next waveform? Clearly, just don't waste time on A and B, because you know that if the wave is coming, then from obstacle here the wave starts bending. Remember, wave starts bending, something like this. And because if we have a one gap, if we have a just gap, two edges, so we have this type of bending. But if we have a one side of bending, that means at the edge we should have, you know, a spreading of a wave. So in this diagram, wave is not spreading. It seems that it is starting from here. Here there's nothing to do with the obstacle, so option A and B are immediately gone, and the rest of the options are C and D. Of course, if you carefully watch these two analyze these two diagrams, you come up with the C. The reason is because according to Huygens construction, every single point on a primary wave or on a wave is a source of secondary wavelet. That means if this is the point, then it will create a secondary wavelet, and if this is the second one, it will create another wavelet. So these points should be at the center of the curve or center of the secondary wavelet, and here this edge is not at the center, it is slightly, you know, closer to this end, but here this is center of this wavelet. That means this is the correct description of Huygens principle or formation of secondary wavelet using Huygens principle. So option is C. A laser light of wavelength 650 10 to the power minus 9 meter is directed at a diffraction lines grating. The grating has 50 lines per millimeter. A diffraction pattern appears on a screen that is 4 meters from the grating. This is the screen distance. Which expression gives the angle theta in radian between the zero order and the first order? So between the zero order and the first order means we have n equal to 1. For diffraction grating, we have most common formula d sine theta, which is the path difference, is equal to n lambda, and we need to find theta expression of angle in radian. Remember, this is the most important thing. When you see angle in radian, then we use just theta, not with the sign. So this expression will be d theta is equal to n lambda, because this theta now is in radian. And now we need to find theta expression for theta. So theta is equal to n lambda by d, and n is equal to 1. So theta is equal to lambda by d. And lambda is 650 10 to the power minus 9. What about d? D is the grating element. That means distance between two slits. So 1, you see, 1 millimeter consists of 50 lines. So how many millimeter? So contains one line. and you see that D should be equal to 1 upon 50 into 10 to the power minus 3 millimeter. This is the value of D. So lambda is 650, 10 to the power minus 9 divided by 50 into 10 to the power minus, no, it's not 50, I'm sorry. I should have, yeah, it is, D is 1 upon 50 into 10 to the power minus 3. Now if you use your arithmetic basic maths, 50 goes up, multiply with this, and 10 to the power minus 3 goes up, so it will become 650 into 50, means 50 is coming up, and 10 to the power minus 3 going up, minus 9 is already there, so it becomes a 10 to the power minus 6. So if you see, you cannot have sign immediately gone because I said that theta is in radian, so don't waste time thinking about that. So 650 50, 650 50, yes, 10 to the power minus 6, 10 to the power minus 6, your option is B. Question number 11. An airport uses the pulse echo technique with radio waves to monitor the position of airplane. These radio waves have a wavelength of about 0.1 meter. State what is meant by wavelength. So wavelength is the distance between two consecutive peak or trough, or you say that distance between two such consecutive points which are in same phase. So that's how you can write. So distance between two such points which are in same phase, that distance would be the wavelength. Determine whether a pulse of 1.5 microsecond would be suitable to monitor the position of an airplane at a distance of 60 km from the airport. So idea is we are going to use this information to find whether this situation is valid or not. Now we use this time to find the distance. That means using this time, how much distance can be observed or can be found. So this is pulse and echo, remember. So S is equal to UT. So S is, U is because they are using radio waves, electromagnetic. So 3 into 10 to the power 8 into time. Time is given 1.5 into 10 to the power minus 6 because of micro. So your distance would be equal to 450 meter. So this is two-sided distance, if you remember, pulse and echo. So this is the sender, goes and come back. So this distance that we calculate is a two-sided distance. So one-sided distance, half of that, which is equal to 225 meter. So using that, we can observe object at least 225. If distance, if object is closer than this, then it cannot be detected. Remember, this is the minimum distance. Okay, and the given airplane is at 60 kilometer, which is is much less than or greater than that 60 kilometer. That means yes, it is suitable. It's suitable. This time interval is suitable. The radio waves are emitted by a source at point X. The radio waves are reflected towards the airplane by a parabolic reflector that produces a beam as shown. Okay, this is a reflector X. Okay, calculate the power of radio waves emitted by the source. Intensity of the beam radio wave is this, and cross area is given. So a straightforward question. Intensity mean flux radiation, or I is equal to power upon area. So power is equal to I into area. So P is intensity into area. So intensity is 0.16 kilowatt 10 to the power 3 into area is 13.2 meter square. So power would be equal to 2112 watt, or you can say 123, so 2.1 kilowatt. That's how you can find the power. Question number 12. A spectrum can be produced by by light from the sun. Discuss why black lines appear on this spectrum. Again, a typical question about energy level diagram and spectrum, these kinds of stuff. Remember, how would you write? You need to, incorporate the given condition in a general answer of energy levels, that an atom exists somewhere. An atom consists or has, discrete energy level when electron stays in the atom, where the electron stays in the level. And then if atom absorbs some energy from outside, from some reason, these electron becomes excited and goes to the higher energy level, and after some time they return, and then they release energy, delta E. And this release energy is equal to the difference between the two energy level, where the electron is jumping from one orbit to another orbit, or one shell to another shell. So delta E is equal to, in general, E2 minus EF. And for every element we have a different size of energy level. That's what you can incorporate in this answer, but you will have to so this is general concept, and this general concept you apply and you just incorporate the condition. Here what is happening, the light coming from sun and entering into our atmosphere, and our atmosphere consists of different types of molecule, and then these molecule or atoms absorb the sunlight, and then electron in the atom absorb these energy, they goes to higher level and then jump back and then emit energy, depending on the difference of the two level. And because there are certain energy levels, so we have a certain different frequencies for black lines. That's how you can incorporate and you can write. Question number 13. A teacher demonstrated standing waves using the apparatus below. The height of the reservoir can be adjusted to vary the length of the air column in the glass tube. So this is some apparatus, air column. This is length, air column length L, reservoir with water or some other solution. Okay, the teacher tapped a tuning fork on the table and placed it above the glass tube, something like this. He increased the length of the air column from 0 until the sound was heard. At this moment, the standing wave was formed in the air column, producing a sound with the same frequency as the tuning fork. When a sound is heard, there is always a node produced at the surface of the water and an antinode at the top of the air column. The teacher repeated this with tuning forks of different frequency f and recorded the corresponding length L. State what is meant by standing waves. Typical definition of standing wave: standing wave is a wave that consists of a fixed maxima and minima, or consists of nodes and antinodes is a better option. So a wave that consists of nodes and antinodes is called standing waves. Now if you see, this is the idea. I just want to explain you what is happening here. Waves, sound waves are produced from this tuning fork. They goes into this air column, and in this air column this behave as organ pipe, musical instrument. So the wave moves so that, like if I draw a slightly bigger like air column, something like this, and you can imagine that you have water filled till here, something like this. So in this air column above the water, above the surface of the water, here in this region, you will find a formation of standing waves. And remember, this is the closed end. At closed end, we always have nodes formation, and the open end we always have antinode. So they are saying that when first sound is heard, so you can visualize situation of formation of wave something like this. This is when teacher heard the first sound. So this is the first sound. So let's just move on. Remember, this diagram is important. The teacher plotted a graph of F against 1 upon L, force, and 1 upon L, not force, sorry, frequency. Explain why the speed of sound in air is equal to 4 times of the gradient of this graph. Clearly, if you see, if you find the gradient of this graph, so gradient of this graph will be equal to rise over run. That means y value divided by x value, and y value is frequency's value, and this will be 1 upon L. And if you simplify this, so it will be FL. And now this is the graph of first sound, and I told you that the first sound is heard when you have a node formation at water surface and antinode at, this is the air column. Underneath you have water here. So if you see, this is the length given in the diagram, if you see, and in terms of wavelength, this is antinode and this is node. So in terms of wavelength, this distance should be lambda by 4. So you can say that since the length of the column is equal to lambda by 4, and you can replace L here. So gradient would be equal to F into length, and length is lambda by 4. 4 goes on the other side, so you have F lambda is equal to 4 times of gradient, and F lambda is the V speed, 4 times of gradient, and that's what they are saying, that the speed is 4 times of the gradient. Show that the speed of the sound in air is about 300 meter per second. So it's a straightforward question again. What you do, you just find the gradient of this line, and then use formula times 4. It will give you the speed. So the best option for me is let's see, I can choose any, so I just need to choose as big as, yeah, this point is suitable for me because I can find the 1 upon L value, which is 5 here, and then here it is 420, I guess. Okay, so I'll take it 420. Now gradient is 420 divided by 5, which is that value, rise over run, and then it is 84 meter per second as a unit, and then velocity is 4 times of gradient, so v is equal to 4 times of 84, which is v is equal to 336 meter per second. This is the velocity. The teacher says that for a tuning fork of a particular frequency, sound will be heard for a different length of the air columns. One point plotted on the graph does not lie on the line of best fit. Deduce whether this point is an anomaly or whether it corresponds to an audible sound. So if you see the graph, this is the graph, and they are talking about this point, and this point we need to check whether it is some kind of anomalous reading, or it is producing some second sound. So if you see the mechanism, if you have a long tube, something like this, a very long tube, and suppose the water level initially was here, then this is the first sound. In the first case that we discussed, this was the L, and if you lower If you lower the water level in the column and water comes here, suppose, that means here we have a node and here we have antinode. The second sound would be heard something like this. This is the length for the second column. Length. And you know that in terms of wavelength, this is antinode, this is node, another antinode, and the node. From A to N, this is lambda by 4. And this is another lambda by 4. And this is the last lambda by 4. So we have 3 lambda by 4 here. So L length is equal to 3 lambda by 4. This is the relation for the second sound. Now the idea is we are going to find the wavelength corresponds to that frequency. We are going to find the wavelength. What is the wavelength? And then we are going to match whether this wavelength correspond to the value of the length showing graph. If it is showing the same value, this wavelength, then we say that this is audible, otherwise it is not, it will be anomaly. So let's find out first the wavelength. So we know that f lambda is equal to v, and lambda is equal to 300 divided by f, and f is the frequency of that point, and this frequency I am going to take as 420, so lambda would be equal to 0.78 meter. And now put this lambda, since for second sound L is equal to 3 by 4 of lambda. Put lambda here, so you would have value 0.585, which is approximately 0.6. Round it off. This is value of L. And then you find 1 upon L, because the graph is between 1 upon L. So 1 upon L, which is equal to 1.709, so which is 1.71 per meter. And clearly, if you see the corresponding value of this graph, this value, it should be 1.7. So 1 upon L corresponds to the value on the graph at frequency 420. So you need to write this statement. So the f equal to 420, at f equal to 120, 1 upon L corresponds to 1 upon L. That means it is audible sound. Question number 14. A light dependent resistor LDR has a resistance of 6100 ohm when illuminated with indoor light. Explain how the resistance of an LDR changes with illumination. Your answer should include reference of conduction electron. It's a straightforward question. Again, we need to relate the light with the resistance. For LDR, remember, a light consists of photon. So if you're increasing light intensity, that means you are increasing number of photon, and when the photon absorbs in the LDR, they transfer energy to the electrons. So the number of electrons are increased, or you can say number of conduction electrons are increased. Conduction electrons are increased. That means resistance is decreasing. A student made an electrical cell using a lemon, a piece of zinc, and a piece of copper as shown. Okay, a student connected a digital voltmeter to a cell and recorded an electromotive force of 0.97 volt. This is EMF. She then connected the LDR to the cell and recorded the reading from the digital voltmeter, 0.47 volt. This is terminal potential difference. Define EMF. So EMF is the amount of energy supplied to 1 coulomb of charge by the battery. So that's what a typical definition you can write: amount of energy, amount of electrical energy supplied to 1 coulomb of charge. Calculate the internal resistance of the cell. Resistance of LDR is 6100 ohm. So you know that E is equal to V plus IR. Since E in the previous part we have 0.97 volt and V terminal potential difference 0.47. So we don't have I, if you see here, but we can find I using I is equal to V by R. So V is 0.47 divided by R. R is the external resistance, which is 6100. So amount of current is 7.7 10 to the power minus 5 ampere. This is amount of current. Now E is it's better to write for internal resistance. So internal resistance, if you rearrange from here, will be R is equal to E minus V divided by I. So 0.97 minus 0.47 divided by 7.7 10 to the power minus 5. So it will be equal to 6.49 into 10 to the power 3 ohm or kilo ohm. This is the internal resistance. Calculate the power transferred by the LDR. Power, LDR, so power is I square into R. I is 7.7 10 to the power minus 5 whole squared into R, 6100. So power dissipation by LDR is 3.6 10 to the power minus 5 watt. Some observations are looking for evidence of planets orbiting a star. Detecting a planet is difficult because its reflected light is insignificant compared to the light emitted by the star. A technique known as nulling interferometry is being developed. It relies on the property of interference produced by the superposition of the two beams of coherent light. Beams of light from the star and from the planet are collected by telescopes T1 and T2. The beams are superimposed using a beam combiner as shown. So this is the diagram. Two telescope T1, T2, both are receiving lights from stars and the planet. So as per key, solid lines are from stars and this star from planet. Okay, beam combiner, both light come here, enters into beam combiner and interfere here. Okay, this is the explanation. So same diagram. Now light from the star would arrive at both telescope having traveled equal distance. A system of mirror is used to increase the path of length of one of the beam by an extra path length equal to half of the wavelength of the light. Now if you see that carefully, if you see the diagram from a star, this is the star. From this distance is these distances are equal, and then this rays come going inside and then into the combiner. But from T1, light first go to some other mirror, and you see here this light is going for some extra path, and this position is creating extra path length, a path distance, a path difference, this region. Okay, so explain what happens when the two beams of light from the stars are combined. Clearly, if you see, when the light reaches in the combiner and they are combined here, there will be a path difference which is equal to half of the wavelength according to the condition, because this system always produced path difference of half of the wavelength, lambda by 2. So between these two waves combining, we have a path difference of lambda by 2, and this is condition for destructive interference. That means there will be a dark spot or destructive interference or no light from the sun from in the beam combiner or at this position. So we have a destructive interference due to path difference of lambda by 2. Light from a star would arrive at, oh no, sorry, this is the same thing. Now, part 2. The two beam of light from the planets arrive at the telescope at slight angle, so that beams have traveled different distances. If you see that picture, the dotted line are showing the tilted path or slightly slant path. That means there must be some path difference between these two even before entering into the telescope. So there is a path difference. Slight angle, the beam have traveled different distances. Explain the condition that would result in this light combining to reveal the planet. Now you see that when the lights are coming, so if the path difference between these two light before entering into combiner, before entering in even into the telescope, I would say, before entering into the telescope, if the path difference between these two is lambda by 2, and then we know that after entering into the telescope and going through the whole process, their additional path difference is produced, lambda by 2. So the total distance, the total path difference, if you combine the total distance, it will be equal to the lambda. That means the light of the planet, when entering and combining in beam combiner, they will produce a constructive interference or maxima. So what is happening? The sunlight is producing no light because of destructive interference, and in this certain condition, planet is producing maxima. So that means we can detect existence of the planet, because sun cannot be detected because of the destructive interference. At present, nulling interferometry has been demonstrated in laboratories using infrared radiation. Explain why it will be more difficult to demonstrate the effect with the visible light from a star. If you compare the radiation, because we are using infrared and visible light, so there's a difference between wavelength. So visible light has a shorter wavelength. So for infrared, because of the larger wavelength or large wavelength, it is easy to produce the required path difference. If you see the diagram, if you recall that we are producing in one of the beam the additional path difference. So this additional path difference is easy to produce for infrared because of the larger wavelength. For visible light, because visible light is already has a small wavelength, so it is very difficult to compensate or to produce this additional wavelength. That's why infrared is better or is used instead of visible light. Thank you very much. I hope you understand. See you in the next part. Have a nice time.